I went on the title, right?
Okay, I'll just wait for one more minute, then start again. Okay, let's get back to it. In the little 3-minute break, when I think about it, proving this proposition is like maybe a good idea for you to try, but maybe it's not like crucial. It's pretty similar. So I'm actually gonna skip the proof. I believe I have proved this. This is the proof is like theorem 2.27 in the course notes, but it is there's like nothing surprising there. Okay. Let's just move on, and hopefully we could talk about different things. Okay. So let's talk about the restriction and the inverse. Okay. Let A be a set. Let F be a function. Define F restricted to A. This is going to be the set of order pairs X, Y, such that X, Y is in F and X is in A. And we can just write a few facts about the restriction. The domain of the restriction is just A intersected with the domain of F. And F restricted to A is a function. I guess there's like one more kind of basic fact you could say. You could say that the restriction to A equals F if and only if, I guess, the domain of F has to be contained in A. Okay, so we can restrict functions to have smaller domains, just like normal. Okay. Okay, and the last thing we'll talk about today is, well, remember the definition of R inverse is just those y-x's such that xy is in R. Okay, so we can ask, when is F inverse a function or a function F? And then the answer may surprise you if you've ever had to prove, like find the inverse of a function. I guess if you've read this part of the course notes, you know the answer. But does anyone want to guess what the answer to this question is? Oh, I don't have the chat up, so I don't see if you answer. Okay. Yeah, okay, that is the answer that I was looking for. But yes, so, you know, if you ever see this question, like prove that F inverse exists, you always do the same thing. You check, is it one-to-one, is it onto? If it's those two things, then an inverse exists. The only thing is that like we have embedded the definition of domain and codomain into our functions. In particular, if I just tell you that F is a function, one-to-one makes sense, but you can ask, like, the question is like onto what? Like whatever our function is, it's automatically onto its own range. Okay, so by doing this definition, this weird definition, we don't have to check if it's onto. Okay, so let me just write our proposition. And after I write down this proposition, I'll just give you an example to tell you what I mean. But let F be a function. Then F inverse is a function if and only if F is one-to-one. And if f inverse is a function, we have the equation like f of x equals y. If f inverse and f are functions, f of x equals y if and only if f inverse of y equals x. Okay. Okay, so we have this proposition. Let's do an example to see what I mean about like why is it we can just forget about being onto? Yeah, let's just do a quick example. Let's take f. I don't know, this is my function. Okay. Let's determine if f inverse is a function. Well, f inverse is just the binary relation you get by switching everything. Basically, switch everything. 0, 1, we switch it. We switch it. We switch it. Okay. This is also a function, right? Because there's no repeats of the first entry. Okay. Which is a function. You know, and we can compare the domain and codomain. The domain of f is 0, 1, 2. The range of f is the domain of f inverse is just 1 to pi. Okay. Okay. So f inverse is a function, but here is where onto might come in. Suppose we think of that f goes from the domain 0, 1, 2 to the real numbers. Now f inverse does not go this is not right. Because the domain of f, or the domain of f inverse, is much smaller than the real numbers. Okay. So this is when we care about if a function is onto. Like if I write f goes from a to b, for f inverse to be a function from b to a, it has to be onto b as well as being 1 to 1. Okay. All we can do is just say f inverse goes from 1 to pi to 0, 1, 2. Okay. Okay, and this just we can just maybe summarize this. I'll try and summarize this with a few statements, right? Like let f be a function. F is defined on its domain. F is onto the range of F. Okay. So that's why we only have to check if a function is one-to-one. I realized I didn't actually write down the definition of one-to-one, but I'll do that now. It's just the usual definition. F is one-to-one if for all A and A prime in the domain of F, F of A equals F of A prime implies that A equals A prime. It's just the usual definition of being one-to-one. Okay, so if a function is one-to-one, its inverse is also a function. Okay. Okay. So if f is a function, and f inverse is a function, then f is called invertible. Right, and then the last thing we want to say about inverses of functions is just the usual thing, which I guess we should call a theorem. Well, part of this I already wrote down. Let f be a function. F is invertible, meaning f inverse is a function, if and only if f is one-to-one. Okay. If f is invertible, then f inverse is invertible, and the inverse of the inverse is just f. Okay. And just to be clear, this doesn't mean that you can go back to calculus or whatever and say like, oh, you know, we don't have to check that it's onto, it's from set theory. No, you still have to. It's just, for us, the question is f inverse a function? And the answer is yes, if it's one-to-one. The question of what the domain is, well, the domain of f inverse is just going to be the range of f. And if you're talking about like functions to the real numbers, having a domain that's like, you know, 0, 1, like some small set is not really useful. So, you know. Okay. I hope that that was more illuminating than confusing. I guess that's it for today. I still owe you guys a lot of things. So I hope to cut down on that soon. Okay. I guess that's it for today. Thanks everyone for coming. I will stop the video now.